I am Dr. Fernie Euclid, Professor from the Department of Computational Intelligence, SRM Institute of Science and Technology, Katanglatur. We will see about the topic trees, introduction onto trees and tree travels. We'll see it first. So first, generally, so why do we go to trees first? Okay. So normally we would have in the previous sessions you would have learned about linked list, then stack, queue, etc. So this tree is why we are moving into trees. Tree is also a kind of non-linear data structures. It is not in an ordered way. It will be in a non-linear way. So why we enter into the tree concept? Tree concept normally it will be mainly helpful in for solving the problems for hierarchical relationships. So in arrays you would have seen that an arrays and linked list for representing or for searching the data it is not that efficient compared to trees. So trees will solve many real world problems that are that involves the hierarchical relationships, and normally trees will organize the data hierarchically, and also it is efficient in searching, insertion and deletion. So when we think of a tree, generally you would see a tree, right? It is in the form of, it has branches and it will have some connections and everything. So here also a tree will have some nodes and edges. And when we come to, there are so many kinds of trees. When we come to balanced trees, it solves in an operations in O of log n time. But in array and linked list, you can see that it takes normally O of n time for many operations. So this is the kind of trees you could see. It's a collection of trees where you have root and all the nodes here. And here also you have, these are called as edges, and these will be, and this is not a tree. Why? Because as you can see that there is a loop over here. It is a like an connectivities. Okay, so tree will not end. Okay, it has no ending here. So this is not a tree. And these are the topics we are going to see. That is the root, edge, parent, child, siblings, internal node, external node, leaf node, level, height. And so these are the things which we are going to see it. So first we will see the tree terminology, root. So the root is not, root will be the main starting node of a tree. So this is, and there will be only one root. Okay. So this is the root node A, and followed by that you have many other branches. So A is the root and that will be the only root. And edges. Normally you can see there are so many edges here. Nodes are connected using the link. So this, whenever there is a link over here, it is called as edges. Okay. So A leads to B and C, B has D and E. So these are the edges. And one more thing, tree with n nodes. Okay. That is how many nodes? How many nodes are here? So totally we have 1, 2, 3, 4, 5, and with along with the root, it is 6 nodes. So when there is 6 nodes, you can tell that it has n minus 1 edges. So 6 minus 1, 5 edges. So you can see here 1, 2, 3, 4, 5. There are 5 edges here. And next is the parent. So when I tell A is a root, B is a parent. Otherwise, A is a parent of B and C. Similarly, B is the parent of D and E. Then it's a child. Then you can see B and C are the child of A, and D and E will be the child of B. And then siblings. Siblings is the nodes with the same parent. So B and C has the same parent A. So B and C will be siblings. Similarly, D and E will be siblings. And the next tree terminology is degree. Degree means the number of child per node. So how many children per node is having? So A is having, degree of A will be, B and C are the two child of A, so B and C. So A degree will be 2. B is having 3 childs, D, E, F. So it will have, B is having D, E, F. So it is degree is 3. But similarly, C is not having any child, so 0. D, E, and F is not having any child, so 0. So, and one more thing, the degree of the entire tree will be 3. The highest degree for B is 3. So that will be the degree of the tree also. So if some other node is having the child 4, then that will be the degree of that particular tree. Next is internal node with minimum one child. At least one child should be there. That is called as internal node. So B is having child. So it is internal node. And leaf node. So leaf node means which does not have any children. It is also called as external node. Okay, C is not having any child. Similarly, DEF is not having any child. So it is called as terminal nodes or leaf nodes or external node. Next is level. So level wise, A is in the 0th level, B and C in the level 1. Next level is 2, 3, etc. And height. Height will be the number of, that is the longest path from the particular node to any leaf, okay, to the leaf. Longest node to the leaf. So from A to the, what is the height of A? So this is 1, this is 2, this is third level, okay. So 1, 2, 3, height of A will be 3. For B, it is, see here, B, it is having one level down and next level down. So 2. So B is 2. C, and for and C, D, E, and F, this for C it is 0, and similarly for G also all leaf nodes it will be 0. Why? Because there are no child nodes, okay. And then for B, as I already mentioned, for D it is only one level down, so it one level it has down, so it is called as it has 1. And depth, see, for height you take from the particular node to the leaf. That is what is the height. But for depth, you can see from the root node. That is from the root node to the particular node. That is root node to the particular node. So for A, it will be 0 because A is a root node. But for B, you can see from this node to the particular root node. So for B to A, it is 1. C to A is also 1. But D, E, F, so D2, this will be D2, that is D to B, B to A. So that is 2. Similarly, G to D, D to A, likewise it goes. And next is subtree. Subtree is, you can see here, this is a biggest tree. In that you have D to this, then this is a subtree, this is a subtree, etc. Then a path means from one particular node to the another node, okay. So path will be like you have a path from node one particular node to a1 to ak is defined as a sequence of nodes, okay. So from one particular A to B to D to G is the path. So when you take, you can from A to G, if I need to find a path, I can go from A to B to D. Similarly, length of the path. So now if I take from A to G, then A to B to D, D to G. So the path is 1, 2, 3. Then ancestor and descendant. Ancestor is parent and descendant is the child. Okay. So A is the parent of B and B will be the descendant of A. Okay. And next, so these are the terminologies we have covered. And next we will go into binary tree. So binary tree is a hierarchical data structure which will have almost two children. Okay. So almost two children. So left child and the right child. Okay. So root node is A, B and B, A, B. These are parent nodes are A, B and child nodes also can be considered because A for A, B and C as the child node, left subtree, right subtree. And when I come to, there are four types of binary tree. So that is full binary tree, complete binary tree, perfect binary tree, balanced binary tree, and skew tree. So first we will see about the full binary tree. A full binary tree will have either 0 or exactly 2 children. Normally we can tell it as either it cannot be a, see for C there is no children. So it can be like that also. And or else it can, A is having 2, B and C as the child. B is having D and E as the child. So either 2 children or 0 also. Now characteristics can be no node can has only one child. Okay, it can. And easier to analyze recursively. You can go recursively, you can search over the tree. And normally we use it in expression trees. And the applications involved, anyway, we'll be seeing one by one all the applications in the later slides. But here, as an introductory part, we'll first focus only what does it. So expression trees, it is mainly used for this. Binary tree is used in expression trees, Huffman coding, and also in recursion. Then next is the complete binary tree. Complete binary tree is all levels will be completely filled. Okay, all the levels will be filled. For example, A is having B and C, B is having 2, C is having also. But except that the last level you can leave it out. This is called as leaf node. So this can be called as complete. You can see in this example, A, it has B and C, B has D and E, C has G and F, and then it comes like left to right, it gets filled. And the characteristics will be it has an efficient memory usage. Binary tree will be having efficient memory usage, and it is used in the array representation. Okay, and the applications will be binary heap, etc. And perfect binary tree means from the name itself it is identified that it has exactly two children, and all the leaf nodes are at the same depth. Exactly two children and all the leaf nodes are at the same depth. You can see here it has two children and all leaf nodes are at the same depth. Okay, and number of nodes you can represent as 2 power h plus 1 minus 1. Leaf nodes 2 power h, where h will be the height of the tree. And the applications which include is decision trees, then math, it can be used in mathematical modeling, tournament trees, etc. Then balanced binary tree. So balanced binary tree, we will be learning it later. There is a formula for calculating the height of the left subtree and the right subtree. Based on that, we tell that whether the tree is balanced or not. So here it includes AVL trees, red black trees. So the advantages will be it is mainly used in faster searching, faster insertion, and also it can give a guaranteed logarithmic performance will be there. And all the time complexities as mentioned, it will be O of log n. Okay, which is very less. And the skewed binary tree will be every node has only one child. It gets left skewed and right. See this ABC left and this is right skewed. Okay. And this will be normally behaving as a linked list. And how we can represent this binary tree? This you can see here a binary tree. Okay, so it has three portions, data portion, left child pointer, right child pointer. Sorry, A is represent and there is a left pointer, right pointer. Since this A has two childs, B and C, you can have left one and right. And here you see here B, D and E, D and E is mentioned here. C has no left, only right. So they have here we have mentioned as not, that is nothing is there in the left, but right you have. And E has no left and right, but D has left and right. So here we have a pointer here. And since G and H has no left and right, it is mentioned as X and X. And you can normally represent a tree as structure node and pointer, left child pointer, right child pointer, and the values which you mentioned can be in integer type, and others can, left child and right child pointers can be in structure type. And so this is the linked list representation of tree. All the indexes are mentioned here. And you have a left child, right child, and all the nodes mentioned here. So you can see here, if you take this node G, you look into this diagram, node G has no left and right. So it will be minus 1 because it does not have left and right. And A has a node A has a left and right. So A has left and right. So left child is actually B. So you look into the index here, node B, which has the index 5. So 5 is mentioned here. And it has the right child C. So C is here, node C, and its index is 8. So the right child 8 is mentioned here. And next come to F. When it takes F, F has no left and right. So -1. Then B. When you take B, it has both left and right child. So B's left child is D. So D index is 10. So that is mentioned over here. And right index is E. So E has 12. So that is mentioned here. Similarly, the other things. Now till now we have seen about the topics of trees and its terminologies. Now we will enter into the tree traversals. So tree traversal is a main topic in tree. That is traversal. What does it mean? It means that you are visiting every node exactly once in a particular order. It has some sequence. In that order only it can. So normally when we can tell that when we want to traverse everyone, it's not that with you have to follow a rule. You can traverse anywhere, right? But so what are the possibilities of that traversals? So left root right, or right left root left root right, left right root right root left, like this. There are so many six possibilities are there. We are going to see the main thing, how does it follows each day order, and how the tree traversal happens. So in binary traversal methods, there is pre-order traversal, in-order traversal, post-order traversal, and level order traversal. Okay. So next is we will see about the pre-order traversals. So in pre-order traversal, you have to follow the technique. First, you have to traverse the route. Next, you have to traverse the left, and next you have to traverse the right. Okay. So visit the route, traverse the left subtree, then right subtree. These applications, these traversal applications, are mainly used for creating so many copies of trees and any prefix notation. In expression trees, you will have a prefix, right? So prefix notation, it is useful, and also in the tree serialization. Now, when you take this pre-order, it's a very simple example. First, as I told you, this is root left right. So root is A, and left is B, and then right is C. So ABC is the output of it. Now coming to the next another example. Here, this is a bigger example. So root is A comes first, left. So left is B, but in B it is again a root, again a parent, right? So it has a left, D, but that is also having a left. So next it comes B. Uh, that is like this. You have to go 1 minute. You have to go in the order of root left right. Okay. So first root A, left is B, then it is right C. Okay. So here in this example, you can see 1 minute root left right. So root is A B C. Okay. A B C. Now coming to this example, root is A, then left is B. So when left is being printed, but before going to, that is root left right. So root left, this is left. So when you take this left, and if this tree subtrees are not there, then you can go to C. But we have a root left has come, but before moving on to right, you have a node over here. Now this B becomes the parent. That is the like a root. So it's not as a root, as a parent. Okay. So then it has again. So we need to root left. So next will be D. Okay. Now again, this is again, it is not, it has also has a child nodes, right? So again, this acts as the root, and this will be left up, G. So now this is over, left is over, now this. So whenever you process a traversal in a bigger tree, you have to take all the sub trees also. So next comes H. So now this tree is over. Okay. Now this tree is over. So coming to the next order. So this is a subtree, and this is over now. Okay. So now coming to next H. So now considering this is already printed and its left is over, now coming to the right. Okay. So coming to the right again. So next is the right one, because this B is over and this tree is over. Now root, left, then as I told you, right. Right, when it comes, it prints E. But now this becomes the root, but it has no left. So again comes the I. Right. Okay. Now this fully is over. This tree is fully over now. That is, this is fully over now. This is root is already printed and this left is fully over. Now we have to concentrate on the right side. Okay. So right when it comes, again it C gets printed. Now when C gets printed, C is having some left subtrees. So this becomes the root left. Okay, left. Now left is there, but this again has a subtree, but this does not have a left. So left is done again. So right has to be printed J. Now this tree is also over. Now this is also over. So this is Raivo, this is over. Only left with the, so root is printed, left is printed, right is printed. Okay. So it comes to an end. Next, we go to the in-order traversal. Okay. So in-order traversal will be, next we go to the in-order traversal. In in-order traversal, it is left, root and right. Okay. Previously, we saw it was root, left, right. This is left, root in the middle, in order. Whichever, see, pre-order, it's first, pre. So root will be the first. And in order, it is in the middle. Okay. Root will be in the middle. Left, root and right. Left subtree, root, right subtree. Okay. And this also is mainly used in expression evaluation, and also it produces some output in the binary trees. Now, when it comes here, as I told you, it is left, root and right. So left, root and right means first it will process the left, then it will process the right, and then it will process the left, root and right. Okay. So coming to this, if you see the next one, it is left. Left is B, root is A, and right is C. Taking this example, it will come to the left. Okay. So when it comes to the leftmost, when it takes this node A, left is B. But that has a subtree. So it comes to D. That has a subtree. So it will come to the last level. Okay, G. Then it will go to its root. Root is D. Its root is D. Then it will take the right. Okay, H. So this tree is over now. Now this tree is over means this side now it is considered as left. So next will be root B. Okay. Now next it comes to the right side. So right side when it comes, it will take E, and that left is not there. So root and now right. Okay, I. Now this fully is over. Left fully is over. Now root. So A will be printed now. Now this is also over. Now the right, you comes to the right side. When it comes to the right side, this will become a root, right? That is then, but left it has to take. But again, this will become a root. So it has no left. Okay. So what will happen? Left is not there. So it will print F first. Then it will go to the right J. J. Now this is over. Now this part is over. This tree is over. Now its left is over. So now this root has to be printed. C. Okay. And this in order is also called as, you can tell it as projection. That is squishing. That is, it can take from the right order, like as I'll mention here. You can see this, it takes like this. It takes like, I'll you could see here, it takes this way, projection. D, this is H. It takes in the same order. It takes this level wise, same order. Okay, so this is called as quishing. You can take it in the same order. So next is post order traversal, that is left, right, and root. Okay, left, right, and root. So you have to keep this all in mind, left, right, and root. You can visit the left subtree, then the right subtree, and then the root. This main application is postfix generation and memory deallocation. These all are done by using this. Now coming to this left is this P. Then right is C. Then the only A will be visited. Similarly, here left is it comes to the leftmost because it starts from A, but it has a left, it has a left, it has a left. Then it moves to the right H, then it moves to D. That is the root. Okay. Then this becomes the left. Now this has to come to the right. Okay, right, when it comes, when it will come to E, but that will become the parent, so it will see its left, no left. So next right will be printed, then only it will go and print the E. Okay, now this left is over, this right is over, now this root B. Now this is considered as left, this fully is considered as left. Now it will come to this right. Right, when it comes, it will come to C, but it is the root, no parent. It has a subtree. Again, this has a parent, and it but does not has a left. So it will take the right. And now this is over. And now after right, it will be root. So F. Then now this fully is over. So this will be considered as the left part. And now the root C. Now finally left is over, right is over, and finally A is left out, root. Okay, and next is the level order. So this will visit the nodes level by level using a queue concept is used here, order by order. So this is breadth first search is used, and here network routing is done, and it is also used in the shortest path algorithms. This all we'll be seeing it later slides. Now level wise order, it goes level by level. So you can see here, it goes with level by level. That is this level A, then this B and C, then D, E, F, then G, H, I, J. It goes level by level. Okay. See here A, B, C, then D, E, F, G, H, I, J. It goes level by level. So till now we have seen about all the four types of traversals. And now what are the uses of trees? So as I told you, I mentioned earlier, it is used for manipulating the hierarchical data. It is easy for searching, and in sorted list of data also, it's very easy to manipulate and mainly used in router algorithms. And next is the application of trees. So applications, anyway, we are going to see it in a separate topic. But before that, mainly it is used for to represent the org. We'll see some few applications along. In all organizations, if you see, you could see in a library database and a student database, it will be in your colleges or universities, it will be according to your register numbers. Libraries, it will be according to the books sorted order. And in patient database, it will be in ID order. So like this, everywhere there will be some kind of sorted order. That is what its organization. In computer files and systems also, you could see it, and it will be all the files will be in folders level as a sub hierarchy. So if you want to find a word or in a file, it is easier to find it out. Then next is to find the Google Maps also, it is very easy. And also networks to find the best path means when you want to watch a YouTube or anything, if you search, what it will happen is the routers helps to find out everywhere it searches, and it will find out wherever it is, it will travel to your computer by passing through many computers called routers. So the routers mainly will be using the tree concept only. Okay, so these all we will be seeing in the forthcoming videos. So thank you.